Okay, anyway, so when it comes to atomic quantum, you're seeing a little bit about, I mean, I hope you kind of find this interesting. The damnedest thing is that once you get past the hydrogen atom or hydrogen-like atoms, we don't know the wave functions anymore. So you take atomic hydrogen ones and then try to fix them, which is what you're doing in your problem set. So you're getting a taste of what theoreticians do. This is a branch of theory to just optimize these functions. And it's useful because drug companies use these softwares for drug discovery. Intel uses it to make better chips. They need to know these optimized functions, right? Since we don't know the real functions. So this is valuable. This is what they do. However, when, I was thinking about having you do some molecular the same thing but for a molecule. What you get into is you actually get in a whole other break. To do quantum calculations on molecules, given these approximations, it's actually a different class. Like you've heard of, I've asked before, you've heard of Gaussian, QChem, games. These are software packages. Some you have to pay for, some are free. And you can draw a little molecule on a GUI. You hit go, it does whatever. To understand what it's doing, it's really a separate class. And I say that especially because you don't really have to have a deep level of knowledge of quantum mechanics to use that stuff. It'd be better if you did. And in fact, I think that the companies make it too easy. It's kind of bad that it's so easy to use, but regardless, when you're doing molecular quantum mechanics on these software packages, which is how you would do them, you run into different concepts that you need to understand. Like when you're optimizing that hydrogen, the helium thing, that's called a basis set. So they have different words. And depending on how it was optimized, if you optimize Z, like you're doing in your homework, that's good for some problems, but if you optimize some other property, it's appropriate for other problems, meaning different types of molecules. So that's the kind of stuff you start learning in a class based on molecular quantum mechanics theory using these software packages. It kind of doesn't have that much to do with this class. So that's why I'm shying away from it. Now, what if you emailed me and I found and mentioned I saw a problem, which actually I'll mention that in a second here. That actually catches me every now and then. But now, how are you folks doing okay, or is it hopeless? Yeah? Or you haven't started? You haven't started yet. That's more accurate. Okay. All right. Given what I just said at the beginning of class, please start on it. It really isn't that bad. And I'll just do one quick little, one person mentioned something, I'll do a quick example here in a minute. But please start on it. Now, again, I said it's a little wishy-washy on an exam, but the head of the division asked me to have an exam, so you really should. I realized what I got flummoxed was in undergrad, I usually have exam 1 at this time, exam 2 a month from now. What I usually do is exam 3 and the final are back-to-back. And I do that just so that they can get more points. And that's a little sucky, especially from my perspective. I have to grade it all. So here, that's why I was a bit confused at the timing. We just won't have an exam 3. Your final will just be the final. There won't be an exam 3. But so anyway, so we should have an exam this Friday. Now I started writing it, and so yeah, your homework and the exam due on the same day. That sucks. But what I'm doing is I have 5 questions. 2 of them will come from this problem set, from like the derivation. Now, you'd be thinking like, well, I can't derive all that, that's crazy. Trust me, I'm keeping this simple. So right now I have half of it's descriptive, like, okay, why is it reflecting this way? I have can you separate the Hamiltonian? That's kind of important. You've seen that happen a couple of times. I'm giving a very simple separate dx dy kind of problem. Then I have, what am I doing? And then I'm asking questions from this problem set, two questions, but they're like descriptive, like, oh, why did I do this? Right? You don't have to sit down to write, you're not going to solve that freaking sum of spherical harmonics, which sucks. It's relatively, like I say, it's descriptive. So if you read through it and kind of followed it, you should be able to do it. Anyway, the big picture is really easy. Okay. All right, so real quick, let me point out, a lot of you haven't done this, but let me point out, oh, that's funny. Number 2 in the grade. I guess unless the caps will be off, I'll be real careful with that. Okay, so let me point this out, because this used to catch me up too. Let's do kinetic energy, and I don't quite remember. All right, so, and I think I mentioned this a few times, kinetic energy, I'm just making this up. I think this is right. Is this right? The kinetic energy radial has 3 different forms. And I never remember, I don't remember them. Anyway, it's something like this. Okay, so now remember that a Hamiltonian on a wave function should give the energy times the wave function, but that assumes that the wave function is the wave function of the Hamiltonian. You don't get that in this case, and that's why you're doing the expectation value way. So what I'm doing is I'm explaining how the trap works, where energy isn't, in this case, the energy, as I explained before, is too high. You're using the wrong wave functions because we don't know what the real helium atom wave functions are. We don't have a clue. You're using the wrong ones. That does give you an energy, but it's too high. One of the things I do like about expectation values, I like how it just spits out a number. I do like that because what can happen is, like with undergrads, when you're trying to do expectation value, you can actually get the normalization confused with the eigenvalue. I mean, it's stupid, but it's an easy mistake to make, whereas this just spits out one number which you can take to the bank. Okay, so anyway, so that's why you're doing an integral. And I also had you, of course, do this. But make sure that you include the Jacobian. So when I was like writing this problem set, I was making sure, I mean, I happened to Google, I know what the answer already is. And I couldn't reproduce it. And what happened was I was forgetting R squared. I do it all the time. That's why I made you do it too, just to kind of make it stick. Okay, but now here's the question. Get away from me, cat. Is that part of the derivative? See, now you don't know, do you? Because that'll change things, right? Now the last homework, that again, you aced if you did it. I had you do this over and over again to make sure you get stuck that product. So the thing with the quantums, the product rules keep showing up all the time. And I'm just trying to get you used to that. Okay, so let me ask you this. Is it part of the derivative? What do you think? Huh? I mean, there it is, right? Derivative, wave function, it's sitting right there. So what do you think? Yes. See a yes back there. Okay, yeses. Yeses, raise your hand. No's. No's, raise your hand. The no's are correct. The no's are correct. It is not part of the calculation. I mean, I know as written it should have been, but it's actually not. Now here's how you figure that. So for one, I'm just telling you that. There you go. Now you know. Right. Number 2, how do I know? It's in the Hamiltonian, right? The Hamiltonian has this operator. The Hamiltonian doesn't have this R squared. It's not integrated. So there's no R squared. So this is in the Hamiltonian. So therefore you just do this. This integral, right? So remember, we want to do things this way. We want to, but we have a weird problem that our wave function's wrong, so we don't have a choice. We're having to do it this way. I'd rather not. The Hamiltonian, as it stands, if we were lucky and knew the right wave functions, you would just be doing this. There is no R squared, right? There's nothing's being integrated. That's how you know that the proper calculus is just to do this. This comes from the integral. The integral has nothing to do with the Hamiltonian. Again, it's just a means to an end that we would rather avoid but can't. So the integral, the R squared, the Jacobian, is really part of the integral. It's not part of the Hamiltonian. Therefore, do this and leave that alone. Do this, R squared, do that, divide by R squared, multiply by that. Whatever all this is, then do that. Anyway, that's how you know. It's a very easy trap to make. It's perfectly, if you did it the way half of you said, I mean, as it's written, it's correct, but it ultimately isn't for the reason I just said. Okay, so do we need a Tuesday review? Or are you happy you don't know? A lot of you are saying yes. Okay, so we'll do a Tuesday, even if one of you said yes, we do it. So we'll do a Tuesday review. And it might be helpful if I just go through it again. Sorry. You tell me whether you need me to talk about wave functions of helium or maybe the specific operators. Now, or maybe I can even do some Mathematica that's on my computer. Any other? So again, sorry about your homework, but again, if you answered the question, you got it right. It's just a lot of you didn't. A lot of you just skipped questions, so don't be doing that. I'll make sure I'll bring your homeworks next time. So come by, or just email me. I'm halfway through grading the last one. So, any other questions? Yeah, we're okay. Alrighty. So, like I say, I don't do too much with atomic wave functions in this class. Try to stick to fundamentals, and so I'm thinking I might just throw in a question about atomic wave functions. The way that you have the spin wave functions antisymmetric for singlets. For triplets, you have the space antisymmetric. Antisymmetric means that you follow the Pauli exclusion principle. Anyway, I'll put these into problems that's kind of agreeable to make sure that you still know this stuff. And again, please remember, please read chapter 1 because that's what we're doing today. Today is Dirac notation. Okay, so where Dirac notation would be useful is not, so those integrals like you're doing on Mathematica, you're not avoiding those with Dirac notation. They're very specific. Right? Dirac notation doesn't magically do atomic integrals for you, but I can give you one example of so here's the spin part, and the Hamiltonian had 5 terms. So remember I was telling you that with Hamiltonian and then the complex conjugate of the same, you don't need to write this down. 2 terms, 5 terms, that's 10 times 2 terms is 20 terms. Okay, now you may notice on the problem set, you ended up with 5, right? So there's 20 terms here, but on your homework, you actually only did 5. 2 kinetic energies, 2 Coulomb energies of the electron within the nucleus, there's 2 electrons, and then 1 between each other. So somehow this 20 gets turned into just 5. That's what Dirac notation does. Dirac notation is what simplifies, so you're not going to actually sit down and do 20 integrals, because 15 or 0. And that would suck for you to do what you're doing times 4 just to find that 75% of it is just 0. Dirac notation gets rid of all of them before you even get to that point, leaving behind the ones you have to focus on. So that's what this stuff is good for. But it's not going to like tell you what the exact value of the Coulomb operator is. Okay, so let's take a wave function and let me kind of show you ahead of time what this is going to turn into. All right, so that's a wave function, that's an easy one. And in Dirac notation, this is what it is. So that's kind of, that's it. Now you're looking at that like, oh, okay, now don't worry about it. I'm actually showing you where we're going to be in a week. That this will be second nature to you. Okay, now let's do overlaps. Now you know that, here I'll label this with an L, like an L wave function. And that's L prime, these are different wave functions. Okay, now if these are wave functions of an operator, if I said wave functions, then they're eigenfunctions of the Hamiltonian, or maybe they're eigenfunctions of a different operator, The operators that we're largely seeing, and this is in my silly textbook, they're called Hermitian. And Hermitian operators are either normalized, so that this is 1, if these are the same wave function, or they're 0 if they're like ground state, excited state. Right, so if they're different, then everything's 0. If they're the same, then it's 1. And you represent that with a Kronecker delta, not the delta function that you saw earlier, the Dirac delta function. There's 2 delta functions. This is just 1 if L prime and L are the same, and it's 0 if not. So that's a Kronecker delta. Anyway, that's kind of an undergrad level. Hopefully you've seen that. Okay, so what this is in Dirac notation is this. Okay, so that's nice. Okay, and then what about this? Okay, I would want to do the same wave function. It doesn't quite make sense to have different wave functions on left and right of the Hamiltonian. That's weird. Okay, and this is what this is. Okay, so that is the Dirac notation for this. So you can see that we're going to simplify, especially these integrals. It is so much nicer to not get distracted with integrals and partials. Oh, where's r squared? Where's theta? Instead, it's just that. And you can kind of look more carefully at what the integrals actually are, rather look at what is going on quantum mechanically than getting distracted with all the mathematics. Okay, now there's some language you got to learn. Okay, so that, we're going to start here. That is a ket. Okay, so let me write this down. Ket. Okay, it's a made-up word, I guess. Okay. This is a state vector. So that you got to learn this language. Right? You're going to see this all the time. In Gilbert, that's awesome. Space. State vector in Gilbert space. Okay. State vector means you're describing something. Here, this is a wave, so I'm assuming it's an electron. So it's an electron, and this happens to be a free space flat potential wave function. So this is clearly describing an electron in a one-dimensional empty universe. So this is the same thing. One-dimensional empty universe. This is every quantum mechanical bit of information about an electron in an empty universe, if that's what I'm describing. It could be all information of a quantum mechanical level of my cat, if my cat is the state. What is the state of my cat? Okay, so that part's simple, but what the hell is Gilbert space? Okay, that's a fancy term for the following. I can have to admit, I do actually find it useful. Okay, my cat lives in X, Y, and, well, sorry. Tell you what, let's do the electron. Hilbert space for the one-dimensional electron is X. That's Hilbert space. My cat is a three-dimensional cat, like I am. Hilbert space is X, Y, and Z. All right, so, right, it's kind of stupid. Kind of. Let me show you where it's more interesting. Hilbert space is up and down for electron spin. You see, you can actually turn abstract under the right conditions. So I'm talking about spin up, spin down, just like our helium case, right? Helium, the ground state, is 1s2, which is this. 2 p's are not occupied. That's the helium ground state. The electron wave functions, alpha and beta, are up and down. So that's the Hilbert space for up, down, for our alpha, beta wave functions. So you can see, I mean, X, Y, Z, okay, anyone understands that, but it can get abstract too. So I think that's kind of cool about it. Okay, now, the way all this got discovered, and we're going to spend a month describing this one thing, which is kind of fascinating. Okay, so this is a fire, big fire. Okay. And in it are Ag atoms. Now, they're very energized because the flame is hot, and there's a slit. In the back, everything's under vacuum. There's a slit. Now, some of these atoms happen to go in just the right trajectory to get through the slit. Sorry, that kind of bothers me. Here we go. There, that looks better. It has to be perfect. It's a little warm a little bit. Okay, so sometimes a silver atom happens to want to go in the right direction, whereas for the most part you're just plating everything else over here with kind of expensive silver. Okay, now over here are some magnets. North, and then a very oddly shaped magnet, the south pole of the same magnet is like that. It's at a sharp tip because it actually makes the magnetic field a little stronger. That's why that's done, in case you're wondering. And as hopefully you are used to in science, we put an eye for a detector. That's how we represent that. Now silver, again, your PhD chemist, right? You should know how to read atomic configurations, krypton core, 4d10, 5s1, still heavy. Okay, so funny thing about filled orbitals, when it comes to electron spin, it's a source of magnetism. Remember that magnetism, like the kind of magnetism that generate power plants, that make electric motors run, that are on your refrigerator, are due to electrons. Electrons that are not paired. When electrons are paired, the magnetism is completely canceled. When two electrons are in the same orbital, there's absolutely no detectable magnetic field coming from them. But when they're unpaired, the magnetism from an electron is oddly quite powerful. Again, that's how we make our power plants, right? So, so we have a 5s1 configuration. So that's a neutral silver, and that makes it magnetic. Okay, so now what? Okay, this gets really complicated. So because it's magnetic, and you don't have to write all this down. I just want to make sure you see all this in case you ever need it for some reason. Okay, so this is the magnetic moment. Where S, this is the spin. Okay, so let me make sure I know what I'm saying here. Charge of the electron, 2 to 2, mass of the electron, speed of light. So it's kind of funny that the speed of light shows up in this. S is spin, so that's literally up or down, plus a half or minus a half. And so you can see why the Gilbert space is just up or down. It does get a little abstract, but we're going to deal with it when we show you exactly what we're doing. The potential energy of something that's magnetic, like an electron, in a magnetic field is going to be the magnetic moment dotted into the B field. So notice that these are actually vector quantities. So sometimes, whenever I'm dealing with vectors, dot products, I just have to look at Google to remind myself how I'm dealing with it. Okay, so anyway, so the electron is a magnet. It's in a magnetic field that's up and down. It experiences a force. Again, hopefully your basic knowledge of mechanics is solid. Minus the derivative of the potential with respect to distance is the force. So that's the force. I'm not even worried about it. It is. So I'm going to actually use these equations. Okay. Now what you would expect is, now remember that silver is going to plate stuff. You're going to see it real well. You're going to see it real good. Okay. So let's say it's spin up. Well, it might be spin up or spin down, right? Now the damnedest thing is, no matter which way it's pointing, sometimes it can do this, sometimes it does that. Oh, here, let me, like this. Now if you're doing this, you're definitely going to be deflected, you know, one way or the other, right? As you move, you're going to be doing that. Or maybe if you're spin up, maybe you're going to be doing this, right? But if you're like this, or like that, your magnetic moment is orthogonal. So you just fly right through. Now my guess is there's only one way to be fully up, there's only one way to be fully down, but there's kind of like an infinite number of ways to be like this. So for the most part, most of them are just going to shoot right through. But some are deflected up and some are deflected down for the reason I just said. And you expect that. Okay? Sound okay? Okay. Nope, you don't do that at all. You should. Remember, this is why the field of quantum mechanics exists. Actually, this is just an experiment for what started it. Here's what you get. Up or down. So the ones that have their electron pointing to the side, it doesn't seem to matter. So let's call that SZ plus, SZ minus. So if you're interrogating, let's call this magnet, you know, we're going to call this a magnet in the Z direction. We can turn it on its side and do X and Y. It behaves as though there's only two states. Now, a vector model says, I get that you can be up or down, but any vector in 3 dimensions can be 90 degrees too, but it seems to just not respond to that. And again, that's incredibly weird. Now, and this is also where quantum, you know, I can't give you a folksy explanation. We're like, well, it's like a car that's drifting. No, I have no explanation for why most of them don't shoot through, even though the magnetic moment, so I'm not saying, oh, so the magnetic moment isn't like this. Oh, no, it is. It is. The magnetic moment can be at 90 degrees, and there's 2 ways to be 90 degrees, actually 4 ways, right? That way and that way. But they're still going to do this. Now that doesn't make, if you're thinking like, well, that doesn't make sense. Right, it doesn't make sense, but this is how it is. And I have no explanation for it other than to show you that this is what happens. And then to do all the derivations after. So there you go. So what you find is that the when you calculate how much magnetism is there, what's the magnetic moment, you find that it's h bar over 2 minus h bar over 2. So h bar just shows up everywhere. You can actually calculate h bar for this. Okay, so there you go. All right, next bit. Next bit. All right, let's see if I can keep going with this. All right, so let's build a block. We're going to build a block for the. We're going to block the spin down ones. Okay. Now what? Now what? Okay. So then we go through another magnet. It'll also be Z polarized. And what do you think you get? Up, down, or what? Same. No. Spin up. You don't get spin down. SZ plus, no SZ minus. Okay. So actually that part's not weird. If you're wondering like, oh, what does that mean? It means it's not weird. I didn't draw it very well, but instead of like getting another splitting pattern, no, nothing weird happened. You selected the ones that are SZ plus, and that information wasn't lost just because, you wiped out, the ones that were deflected downward, they got hit by a V block. So you still selected the plus ones, and there's still plus one down the vacuum tube. You can actually find pictures of these things online. They're just really long vacuum tubes. Okay. So nothing weird. Okay, now I'm going to have to redraw this. I'm going to have to do this like this. I don't know if I did such a good job. I'm going to simplify the magnet with this little box that's like, this is the experiment. Okay. All right, so now what? Okay, so I'm going to represent it this way. So we're going to do the same thing. So the box is a selector, Stern-Gerlach. So this is a Stern-Gerlach. Oh my God, sorry. Yeah, so 1922 is when all this was done by Stern and Gerlach. Now remember, this is right when quantum, I believe Schrodinger's paper was published in 21 or 22. So all this is happening at the same time. And De Broglie also was writing his thesis about, I think his thesis had just been published as well. So literally all this happened all at once. And I think it's kind of remarkable that all this started coming out, all this quantum mechanics started coming out when people had electricity. When they had electricity, they had new elements because you actually isolate a lot of elements with electrolysis, and you had vacuum pumps. They had vacuum pumps without electricity. Okay, so let's do a Z, Stern-Gerlach, and Stern-Gerlach is the thing I just drew. Okay, so the plus goes through, the minus gets a block. So that's what I just drew for you. Okay. Now if I do another plus Z, then the plus still comes through. But now let's do a Stern-Gerlach magnet in X. So instead of the magnetic field being up and down, which I drew for convenience, instead take the bar magnets and just rotate them. Okay, now if I rotate them, now your deflection is going to be like this. But whatever, I mean, it's not hard to imagine. So I'm just going to say that you're going to have X and Y, you're going to have plus or minus, but rotated. Okay, what do you think? So again, these are, they went up or down. The ones that were down were selected out. Now they're going right and left because the magnetic field is coming at you. 50-50? 75-25, 0, 1, 1, 0. What do you think? So again, we're going to have plus or minus. What do you think? What's the relative population? 50-50, sure, 50-50. Okay, 50-50 split. Not hard to imagine, it's a different dimension. Okay. Okay, now let's do this. Block the negative like we did before. Okay, here's another Stern-Gerlach. I hope we make this S now. Okay, now it's back to Z. Now it's back to Z. What comes out? What do you think? Plus minus, all minus, 50-50, 75-20, 25-30-25, 25-75. What do you think? What do you think? 50-50. Right, it's 50-50. Okay. 50-50. So here's the thing. Selected out the negative. Now if this was another Z, there's no negative present, but it's an X, but whatever, it's a different dimension. Now remember how we keep saying that dimensions don't communicate? Well, apparently that's not true anymore because you've lost your information. They're not plus polarized anymore in Z. They're not plus polarized. That's been scrambled. So this thing scrambled that information. But now, again, one of the reasons that well, maybe it's like not too hard to imagine, like, well, yeah, you messed it up. Remember, you're in different dimensions, right? We've been talking a lot about how different dimensions don't affect each other, but now I'm going back on that because they do. And I am going back on that because they do in this particular quantum system. And the one thing it has said is that every quantum system is different. Okay, so nuts, right? Okay, so now it turns out that this kind of behavior has been seen before. Any of you polarizer? When you were little, you get polarizer for light, right? It's polarized. Look at the fish in the water. If you put another polarizer, I mean, you did this in middle school, right? Middle school, high school. Another polarizer at 90 degrees, what do you see? Right, it's dark. Okay, now had any of you ever done this? Put in a 45-degree polarizer between the X and Y. Have you ever done this? What do you think happens? Yeah, light comes through again. Right, so now this one and this one, it's obvious. They cancel. But the effect of this one is basically in comes something polarized in X. Let's say let's call this X, let's call this Y. This is Y. This thing basically takes a vector and turns it into a 50-50 projection, right? 45 degrees. So this vector basically points this way. This is what it does. It rotates the vector 45, but now it has overlap. Now it has X and Y components. So part of the light comes through. Not much. It's actually pretty, now I do this all the time. I have some polarizers in my office. It does work. The light is very dim, all right? But it's not completely black at the same time. So there is a classical analogy for this. All right, now, here's the thing. Now what we got to do is start, this behavior is 100% quantum mechanical. Deeply quantum mechanical. And now we're going to start using quantum mechanics to describe it, and we're going to use Dirac notation because, again, it really sucks not to use Dirac notation. If I don't use Dirac notation, you're going to hate doing these problems. Okay, so here, I'll leave that up there. Okay, so we got to start getting our kets. And another thing about Dirac notation is it's like doing math problems. It's just best to practice. So we're just going to do, we're going to set up like a whole bunch of these and analyze it. And in the process, you're going to figure out what kets are. Okay, so we're going to have a basis set. Okay, basis. I remember I mentioned basis set before. SZ plus and SZ minus. Okay. Now here's where this gets redonkulous. These span Hilbert space. So I'm describing spin of an electron, and it's either up or down. Now that means that everything I do should be described simply with up and down. That's the Hilbert space, up and down. Now, the reason you're probably thinking, oh, well, of course. Now hold on. Z. What about X? What about X up and down? Shouldn't I have an X up and down? And a Y up and down for that matter? Shouldn't I have 6? What do you think? Should I have 6 or 2? Huh? A lot of you said 6. The answer is 2. There's only up or down. Dimensions don't matter. The Hilbert space is 2, up and down. So, and that's just because that's how it is. So now what my job with Dirac notation is to figure out how to describe, but then how do I describe X? And then of course if I did the same thing with Y, I could have just changed all the X's and made them Y's. I could have done the same thing. So now how am I going to describe what happens in X with the Z basis set? How do you do that? Right now, I'm going to give you the answer. And the more you work with it, I'm not sure how to direct this. I know it works. So I'm going to give it to you, and then you're going to do a gazillion problems with it, and you're going to realize this, of course, this works. It works just fine. That's just kind of my approach. It's maybe not the best approach. Okay, here is the top part. Here's the top part. And this is, again, part of the reason I'm doing this is that it explains the experiment. And it gives you an idea of how this actually works. Okay. So the idea is that, oh, sorry, I'm doing next. All right, so for the Z basis set, there's nothing to do. They simply exist. But what my next job is to describe everything else with that basis set, including what happens in the X and Y direction. Okay. So here you go. 2 lessons here. If I know my Hilbert space, if I know up and down is it, I've got to be able to describe every other freaking thing that I can observe using that basis set. Now here, it's just a Stern-Gerlach and X. Stern-Gerlach with Z, there's not much to it, right? If I pass through a Stern-Z experiment, I get an up and down, and if I block this one, it's forever up. Right? So this is perfectly sensible. Where it gets funky is when I start running it through an X. When I run it through an X, what I see here is that I've lost my information in Z. Now, why did that happen? Well, because the X plus is composed of plus and minus in equal amounts. Hence, when I did this, I still had 50-50. I converted back to 50-50 in Z. Hence, an even split when it ran through a third Stern-Gerlach in the Z direction. Okay, now, had I collected the bottom one, had I collected the X minus polarized, I would have gotten the same split in Z. That minus sign doesn't mean anything. Now, the reason that is that you notice I didn't write half, and I wrote 1 over square root of 2. Now, why is that? Right? Now, it's 50-50, right? It's 50-50. Half is that, half is that. Why did I write 1 over square root of 2? Why didn't I write 1/2? What do you think? All right, what's a quantum mechanical observable? What's the probability distribution? Is a wave function a probability distribution? No. The function squared. Right, so you square it, there's your half. Okay. Now you see a minus sign, and that'd be like, well, that means it's not there, or it actually goes up. The down goes up. No. What happens when you square minus 1 over square root of 2? It's positive. Right. So the minus signs don't have it. So there you go. All right. Now here's another thing you can do, is with some algebra that maybe get the computer to do it. This is actually kind of more of a pain than it looks. This actually sucks. It takes a couple of steps. It looks like it should be easy. You can then describe SZ using the SX basis. And again, this is just some algebra. So let's see, I take this plus that, and you kill off these two, and you end up with 2 over root 2 SC. Anyway, so you can do this kind of combinatorial. So notice that with this basis set, there's kind of really nothing you can do. And what you choose to be a basis set is actually arbitrary. We think of Z as special because of gravity, right? Z is special to us because of gravity, up, down. These things don't perceive gravity, but we tend to put them in the Z basis set. But there's no reason for it. It's just a letter. Okay, now I could have also done all the Stern-Gerlach this and that in the y direction. I just chose x because x is easier. But now, and this doesn't mean much. It actually, this is a useful thing that you'll want to use at times for some of your problems that are coming up. But my point here is that what you decide is a basis. I could have started with x as a basis and derived z. It's just arbitrary. So we're going to stick with z. Okay, now here's the thing. Here's another thing about this. And I'm not ready to show you this yet, but it's true. Remember how at the beginning of class I said wave functions, when you integrate them by times each other, times their complex conjugate, that's normalization, it's 1. But if you integrate a wave function times a different wave function, 0. That's orthonormality. Normal 1, ortho 0 if you're not the same. It turns out that this and this orthonormal, this and this integrates to 0, this and this integrates to 0, this and this integrates to 0, this and this integrates to 1. And the same for all the others. Now, I'm just telling you that we're actually going to do that calculation next time. I'm not ready to show you how to do an integral in Dirac notation. I'm showing you how to set up an integral. Next time, I'll show you how to integrate these wave functions times each other, times themselves and times each other to show what I just said. But they are orthonormal. This setup, this is orthogonal to this and that. Now SY, the reason I'm saying that is, I got a few minutes to show you this. SY has a bit of a problem in that I'm not sure how to construct another orthogonal vector because I kind of used up the only good idea I had with X. But you can do it if you're willing to go into the complex plane. So again, using mathematics that we're going to do next time, I will show you that these have the proper orthonormality property. I just don't have, I need to take these in little steps. But this is why this is set up the way it is. And why I have to include the letter I and do complex this and that, because otherwise I can't really describe this. Okay. Now, I'm almost at time. Give me 2 minutes. All right, so just summarize. These describe these describe silver atoms. They really describe their 5s electron. That's either up or down. This part is another state that occurs when I run it through a Z, through an X polarized or a Y polarized magnetic field. It all uses the same basis and they're orthonormal. And again, we'll do orthonormal next time. And so I know that probably doesn't even make sense right now. Last bit I want to show you, and you'll understand why I've been doing some things with matrices, like that homework, which was really easy, right? You can represent these state vectors as you can do a lot with matrices. What? That didn't, right. Kind of makes sense. Up, down, and then SX plus is, so anyway, there's a reason why I had to play some games with those matrices. I know I'm a little crooked. SY plus, we go with this. I don't know why I'm so crooked today. One over. So when we do all kinds of operations in the near future, you're going to be doing Hamiltonians with matrices and wave functions, which are these really aren't matrices, by the way. These are vectors, right? A vector is a single column matrix. So it is still a matrix, but when it's a single column matrix, it's considered different. It's considered vector. So these are the vectors, and later we're going to do Hamiltonians that are actual matrices. Anyway, we're going to do a bunch of stuff. So that's for sure. Okay, so